Again, as I was saying, this is not a hardware class. Basically, we will be trying to cover different aspects related to deep learning algorithms, a lot of practice, and obviously some hardware implications. But let me, in this first lecture, let me try to give some motivation. I'm not sure if you need any motivation. I'm sure you have a lot of motivation. But still, I think just to give you some of the topics that will be covered by this course, I would like to show some highlights. So I think probably the last decade of this century has been marked as the beginning of the era of artificial intelligence. Obviously, people have been talking about artificial intelligence for many decades already, but I think we are now much closer to achieving some of the declared goals of AI than we have ever been. And there are several reasons. Of course, we can discuss them. There are several reasons for why this is happening today, and it was impossible before. So I will try to share my reflections on this briefly. So you can find artificial intelligence in the broad sense. Of course, this is a buzzword that different people attribute different meanings to, but you can find some sort of intelligence or inference capabilities, some judgment capabilities, some decision-making, autonomous decision-making capabilities in many technologies, many devices around us. For example, we already see self-driving cars that are capable of driving many tens or hundreds of kilometers without any human intervention. We see, for example, incredible success in automatic translation technology. So it is still quite difficult to create a coherent translation of large pieces of text. But if you, for example, want to translate a sign from Japanese to English, for example, this is something that you can do with your smartphone. You just take a picture of the sign, and it will simply replace the Japanese characters with English characters. And also, you can speak to this phone, and it will recognize your speech, translate the language, and synthesize the speech back. And all this is possible today. It's not science fiction anymore. This is possible due to different machine learning or AI technology. There is also incredible progress that has been achieved, for example, in computer vision, with applications ranging from web search to surveillance and smart cities. We now wear or have in our pockets devices with quite sophisticated and intelligent capabilities. We have smartwatches, smartphones. Basically, this somehow probably compensates our lesser and lesser ability to keep track of all the complexity of the surrounding world. We have voice assists that we can command with our voice and then can perform some tasks at our home. We basically have smart home devices that are also endowed with some artificial intelligence capabilities. But I think there have been a few remarkable milestones. For example, I'm really impressed by this result. This is the DeepMind AlphaGo 0. It was much less PR than the previous result from 2016 of DeepMind's AlphaGo that basically was playing the Go game better than the human champion. What is remarkable about AlphaGo 0 that this was a totally basically reward system, right, again by DeepMind, that learned to play the game from scratch without human knowledge. So basically, when it started, it didn't know how to play the game. It was just doing random moves. But then it played against itself a zillion of times, and it learned how to play the game better than the best human players. And basically, this knowledge was created by just learning. No, or at least again, we don't know all the details because this is the commercial product, but it is presumably with very little human knowledge involved in the learning process. And I believe this is remarkable. This is probably the closest you can come to real AI. This is obviously just the beginning. Now, why is this happening now? So basically, if you look at different challenges, like for example the visual recognition challenge, you will see that the algorithms that were able to achieve state-of-the-art results on these challenges date back by maybe 50 or 20 or maybe even more years compared to the actual date where the challenge was won. But on the other hand, if you look at the data that was used to train these learning algorithms, basically there is a gap of maybe a few years, maybe even less, before the availability of the data and the availability of the state-of-the-art result. So it's not really about the algorithms themselves, as it seems to be. The visual recognition is just one example. There are many examples like that. So it looks like basically this abundance of data is something that is driving, is propelling the advancement of artificial intelligence. And you know this buzzword, big data. This is just a visualization of the numbers, basically how huge is the amount of data produced and consumed by humanity. So this is statistics for 2017. This is the amount of data that is used or produced or consumed in a single minute. So just imagine that Americans alone use something like over 2.6 million gigabytes of data in a single minute. I think this is incredible. It's really difficult to imagine how much information this is. And something like over 100 billion spam emails are sent in the entire world in a single minute. This is simply incredible. So basically, there are many definitions of what big data really means. It's a buzzword that everyone attributes a different meaning to, but I will give you my own definition. So my definition of big data is more than what you can ever hope to process. So we are simply flooded by data. We don't really know how to make use of all of it. But basically, this abundance of data, this in many applications where we really have such a deluge of data, propels the machine learning and the artificial intelligence technology. And of course, there are some other fields where data is more scarce. Like for example, in medical applications, you only have a certain amount of human patients on the globe. So basically, you will be limited in the amount of data available there. So there maybe we are still challenged by scarcity of data. But basically, to some extent, we can say that our society is tremendously affected by this trend of data availability. And even some people are talking about basically raising this belief in the need of data processing to some kind of religious faith. And I would like to quote Yuval Noah Harari. I think his views are very known. I guess I share most of them. But he's writing the following way in his essay about what he calls dataism. Just as divine authority was legitimized by religious mythologies and human authority was legitimized by humanist ideologies, so high-tech gurus and Silicon Valley prophets are creating a new universal narrative that legitimizes the authority of algorithms and big data. This novel creed may be called dataism. So basically, it's sort of universal belief that basically data is the most important thing and not some religious or human values. So you can agree or disagree with this. Definitely these arguments are probably now one of the most debated ones in all imaginable forms. Of course, the threats and the consequences of artificial intelligence are not clearly understood. But basically, definitely data is one of the most powerful drives that makes this progress possible. Another powerful drive are basically computing technologies. And there was a guy who was one of the founders of Intel Corporation who decreed about more than 30 years ago that basically the technology will advance at such pace that the number of transistors in CPUs will double itself every certain amount of time. I think he was initially talking about 2 years or 18 months. But basically, this has been known as Moore's law since then. And surprisingly, this law still holds today, and it also applies to not only to the number of transistors in CPU, but also to number of megabytes per dollar in hard drives and many other information technological parameters. So basically, our compute power grows exponentially, and this allows us to make basically to crunch the huge amounts of data that we have been seeing that are flooding us, and do something useful with this data. So basically, on top of these pillars, rises this and grows this I wouldn't call it a bubble, but rises this set of techniques and technologies that can be collectively called as artificial intelligence. And basically, there are many problems that can be probably put into this category. What is interesting is that for about a decade, there has been a very prominent player that tackles all these problems extremely successfully. And this player is called deep learning. So let's have a look what exactly deep learning is. And basically, since this term appears in the title of the course, we should better understand what exactly we're going to deal with. So I think deep learning has been defined as a career breaker in many fields of science and engineering. So basically, this is for example, a visual recognition benchmark, ImageNet. What you see on the vertical line, on the vertical axis, is basically some accuracy figure, percent. I think this is the top 5 result or top 10 result on ImageNet. So basically, people have been working on this visual recognition task for many years. Computer vision has been kind of a storytelling discipline of computer science. Basically, we have a beautiful story to tell, but nothing works, or things work poorly. We didn't know how to solve segmentation problems. We didn't know how to solve recognition problems, detecting objects in the wild in challenging situations. It was quite a difficult task. But suddenly, around this point, came a new technique based on deep learning, and basically halved the error rates on this benchmark. And then steadily, so these figures improved steadily over the years, and nowadays we are at the point where computers do this task better than humans. And basically all these handcrafted features, so now we are saying this with some derogatory sense, so basically all these handcrafted features that people spend their careers on doing computer vision research, nobody uses them anymore. You can discover these features from the data automatically better than you and I can do. Very similar situation happened in, for example, in speech recognition. Again, deep learning improved the results significantly, and again, there is a steady progress in speech recognition. Now you can call it a working technology. Of course, there are many challenges, still many unsolved challenges, but let's say, at least from first order approximation, speech recognition works really well. You can easily check it by opening your Siri or your favorite voice assist and talking to it, even without being a perfect speaker in one language or the other, it will understand you quite well. So I think this is quite remarkable. But if you believe, so some bedcomes will say, well, but deep learning is just rebranding of the good old neural networks that exist, I don't know, from depending where you want to count, from the 60s, from the 70s, from the 80s, maybe from the 90s. So basically, this is not new. They existed for ages. So, well, this is just rebranding the old stuff with a new term. But I think this to some extent misses the point of deep learning. So basically, I think what is more important is not the set of techniques themselves that we know nowadays as deep learning and that are based on some kind of artificial neural networks with this or that architecture, or these are on those are algorithmic tricks that people employ today. I think what is more important is the data-driven approach, the approach itself, which I think, even if tomorrow new techniques will arise and will replace deep learning, and there are a few candidates that might eventually do it, I think the data-driven approach will not disappear. So basically, you can think of the data-driven approach as a new way of doing software. basically it appears, and basically our experience tells us that, in the overwhelming majority of problems in the world, it's much easier to identify some desirable behavior than to explicitly write a program that will behave in this way. And probably this suggests that P is not equal to NP, right? It's easier to verify a solution than to solve the problem. And again, we're not going into these philosophical aspects, but somehow the world behaves in a way that suggests us this, I would say, truth. So we can think of a computer program as some map that takes some input space and maps it in some maybe very intricate way to some output space. And basically every program is a point in some huge space of such maps. Okay, so you write it a few lines of code and you create a new map between input and output. And let's say you want to do Fourier transform. So you code your algorithm as matrix multiplication. It does exactly the job, but it's slow. If you want to do it faster, you need to rethink again. And there is some inventive step that required some touch of geniality to invent a faster Fourier transform algorithm. And basically it has nothing to do with the matrix multiplication. It has a very different structure. So basically there is no real recipe on how to do it better. However, what we can do if we have a recipe to verify whether the result, the outcome, the behavior of the program is good or bad, we can just try different points in the program space and give them some value, some loss value, whether they are good or not, and try guiding our search in this space of all possible programs to a point that will give the best map from input to output. And this is exactly what data-driven approach suggests. So it simply tells us that you can, in many cases, collect examples of desired behavior. And if you have examples of desired behavior and some loss function that tells us how well the output of a given program corresponds to that desired behavior, you can search in that continuous space of possible programs some optimal point that will reproduce this desired behavior. And this is what exactly all data-driven approach is about, and in particular, deep learning is about. So basically, we are not writing programs in terms of coding C or some other high-level language. We are basically writing the code in terms of some set of parameters that define very complicated nonlinear parametric functions, mapping from input space to output space. And we are doing a training phase that finds some best configuration of these parameters. And what is surprising that this works. It's surprising because this is a highly non-convex optimization problem. It's a hopeless problem in the sense of the classical complexity theory. It is empty hard. It's impossible to solve this problem, but still somehow it works. There is some magic that is, I would say, poorly understood. We don't really know why it works. So basically, this new paradigm of writing software replaces explicit modeling and deep understanding, deep domain knowledge by learning from examples. And the consequence is that you can take a problem like speech recognition and work on it 2 weeks, collect lots of examples, and solve it better than people did with spending their lifetime careers on deep understanding of the problem and deep modeling. So basically, this is quite frustrating in some sense, but this is something that this is a reality that works out of the box on many real world problems. And basically, this is not limited, as I said, to deep neural networks. This is something that can be done with other approaches. People are basically finding commonalities between deep neural networks and more traditional code, especially if we are talking about functional languages as opposed to imperative languages like Lisp, for example, where basically the program is defined as some composition of functions. It's not very far from a neural network. Neural networks like, for example, CNS, convolutional neural networks, they also use some common methodologies of writing code. For example, weight sharing in deep neural networks can be compared to calling functions in regular code. So basically, what I'm trying to say is that more traditional computer languages can be also adopted to, basically can adopt this paradigm of data-driven learning. Basically, you can differentiate some of the linguistic constructs. You basically can compute their gradients with respect to the changes of the program itself. And this allows training using very simple optimization tools. So what are the advantages of deep learning, of deep neural networks? First of all, unlike traditional software, they really use a very narrow instruction set, if you want to think in this way. Basically, the more or less convolutional neural networks use multiply and accumulate and some simple nonlinearity, basically using saturated arithmetics. As a result, you can easily cross-port them to different platforms. Of course, you might be limited by computational resources, but it's very easy to port some set of matrices and coefficients rather than porting some piece of code. Another consequence of this is that you can make them make them friendlier to hardware. This is not exactly a true statement. There are many nuances that make hardware implementation of deep neural networks quite troublesome and problematic. So we'll discuss this more in during this course. But at least in theory, you have predictable latency and memory use of these networks. Don't have surprises, infinite loops, very deep recursion, and things like that you encounter in traditional programming languages. Now, what is quite remarkable, but not entirely true, but at least it's true to some extent, is that unlike traditional software, deep learning is much more agile. If you want to get better performance from your sequential algorithm, you are more or less stuck. You need to rethink everything from scratch. If you use deep neural networks, just put a bigger network, put more channels, more layers, train it with more data, it will work better. So this is quite incredible. This has no analogies in the old way of writing software. And what is also incredible is that you have a module through which you can propagate derivatives, which allows you to train it using simple, essentially gradient descent techniques. So you can concatenate, you can chain together multiple modules into a single system and then train everything end to end. So imagine, for example, if your your video player did changes to your video driver or to your sound driver to do this task of playing video better for specific content of video. That would be completely impossible in regular software, but this is something that is done commonly in these data-driven approaches. Now, what are the disadvantages about it? It looks like dreams coming true, and in some sense it is. But basically, the main problem, at least if we pretend to be scientists, basically we don't have a clue why this works. And some people are comparing deep learning to alchemy. Basically, we cast some spells and try doing this and doing that, and suddenly it works. We don't really know why. We don't know really why things don't work. We don't know exactly how to guide our search. So of course I'm exaggerating. There is still some good engineering practice that these people try to utilize in this search. But of course you can despise alchemists, but they were dead wrong about everything. But they occasionally discovered things like conservation laws and some elementary chemical reactions. So of course, we know that spells are not enough to transmute lead to gold. We need a nuclear reactor for that, but we know that after about 300 years of study. So it is quite likely that machine learning and AI will eventually converge a stage where we have a much deeper understanding. But I think there is still some utility in this alchemy stage at which it is found today. First of all, because it works. So it's very difficult to argue against results that are really state of the art. And there, of course, there are fields where it doesn't work, and we don't really understand why. I think it is still useful to take these tools with appropriate precaution and use them for your applications, and also concurrently try to understand why it works. It's always better to try to analyze and understand things that work rather than trying to analyze things that don't work. So there is some effort in understanding these systems, but it might happen that we won't ever gain understanding of these systems just because they are too complicated, very complicated. There are some very, very confusing and troublesome features of deep learning. For example, if you take the visual recognition task, you can design inputs that will produce completely wrong results. And you can actually print stickers and put them somewhere in the scene, and these stickers will be recognized arbitrarily wrongly. So imagine basically what it means if you do this to a self-driving car. So it doesn't make me feel very confident, right? But maybe such things exist in biological systems as well. Think of all kinds of optical illusions that confound our ability to make correct conclusions about the geometry of a scene, for example. So we also suffer from such adversarial examples. So of course, what I'm trying to say that these techniques are not perfect. They have their sometimes embarrassing failure, but I think overall this is a very powerful arsenal of tools which we fully understand but still can use in our application.
What do you see in this slide?
Well, so basically what you see here, like you see an image that looks completely arbitrary, but a visual recognizer will recognize it as a digital file. Or this one is an assault rifle, so there is no rifle, of course. But somehow it confuses the classifier. And basically, surprisingly, you can add very minor noise to an image and make it look completely arbitrarily different from what it is to a human observer. Okay? So basically, what are the goals of this course, at least as we see them? So basically, if this is alchemy, okay, so let's learn how to use this set of alchemy tools. Still it's something that requires some mastering. So this will be very, very practical. We are going to learn some ideas and practices behind different tools in deep learning using PyTorch. We are not going to pretend that we fully understand why they work. I don't think anyone trying to understand why they work. There are still some hints of theory. We'll briefly discuss some hints of theory toward the end. And of course, the story cannot be full if we just discuss algorithms and software, because there is some hardware underneath. These are very computationally demanding tasks, both the training and the inference part. And without taking into account hardware limitations and hardware considerations, it is impossible to see a full picture. So basically, we are also going to speak about hardware, not only about algorithms. So let me give you some 100,000 feet view of the course. We are going to talk about deep neural network architecture. This will be our main workhorse for doing deep learning. Basically, we're going to construct artificial neural networks with different configurations or different topologies that in this field are called architectures, not to be confused with hardware architectures that we are also going to discuss. We are going to discuss convolutional neural networks, residual networks, recurrent neural networks, long short-term memory networks. Basically, these are the most commonly used network architectures. We'll see basically what are their main applications and different advantages and disadvantages. We'll talk about I call it art and science of training neural networks. Basically, both numerical techniques and ideas like backpropagation, which is nothing but chain rule that you know from elementary calculus, Basically, this simple idea works extremely well together with stochastic optimization techniques. We are going to discuss it. There are some theoretical insights why exactly it works. Some of these insights is extremely sophisticated and uses, for example, things like stained glass models from statistical mechanics. Some of the insights are easier to grasp. We are going to talk about different numerical complications like vanishing and exploding gradients that we have when you create too deep structures and ways to overcome them. We'll talk about activation functions and weight initialization, about dropout and Bayesian normalization techniques, data augmentation, basically how to create more training data, because the availability of training data will be, as you will see, will be one of the major limitations to all these techniques. We talk about several regimes in which neural networks can be trained. One of these regimes will be supervised learning, which is the simplest and the probably most commonly used regime. In supervised learning, you have some parametric functions, some system with tunable parameters. You present it with examples of inputs with corresponding. If you present an image to this system, you know that, for example, this image contains a cat or a dog, and you expect the system to give you an answer, dog or cat. If the system makes a mistake, this mistake can be back propagated, and you can actually compute the gradient of your objective function that tells you how well you are doing this task with respect to the parameters of the network. Then you can tune the parameters to decrease this objective function, and basically essentially create a network that makes less mistakes. And then once this training stage has finished, you can now fix the parameters of the network and apply it in the inference mode. When new examples are presented and it produces new labels. And some magic happens here, which is basically the main magic of machine learning. So when you did this process well enough, even if you encounter previously unseen examples, you are still going to do a good job. And basically, it implies that there is some continuity or some smoothness of these input and output spaces. So basically, you are essentially solving some kind of interpolation between the training results. We are going to talk about unsupervised learning. So in unsupervised learning, you are presenting the system lots of inputs, but you are not telling what these inputs are about. So there are no labels, no annotation. However, if you are, for example, presenting many examples of faces, you can construct a network that tries to first to encode the data by challenging it through a bottleneck. So you really create some intermediate low-dimensional space in which your data are represented, and then you try to decode from that representation and get the result as close to the original input as possible. So basically, these are called autoencoders. So you're doing an encoder and a decoder, and you're trying to do as good as possible this job. What you get as the result is some intermediate space that captures the nature of the data and throws away all the nuisances that the data have. For example, some pose variability or things like that. So we're going to talk about variation or autoencoders. And this, of course, allows you to build a generative model. So you can now throw the encoder and just put points in this latent space. So for example, if you train an autoencoder on faces, every point here will be a face. So now this decoder system will never produce you something that doesn't look like a face. So you can do crazy manipulations in this space. You can, for example, do metamorphosis of faces. You can synthesize new faces based on partial data. And basically, you are going to be restricted to that very intricate subspace of faces. Basically, you are discovering the structure of the data without any labels. This is the hallmark of unsupervised learning. Now, if we are already building generative models, so here a generative model is trained using some similarity between the input and the output. And of course, you can argue what exactly this similarity is, but usually you use some simple, normal, like the Euclidean distance between the input and the output. But you can say that I don't really know what this objective function is. Let's learn this objective function together with the rest of the system. And this gives lead to what is called adversarial training or generative adversarial models. Basically, you can create a generative model, a generator that creates data, and you want you want these outputs to look exactly as real data. So you put a discriminated network, a classifier essentially, that receives outputs either from the generator or from the real distribution of your data, and then it tries to classify them. Either they are fake or not. So basically, either my generator is an imposter or not. And you train both the generator and the discriminator together. So basically, if you think of the discriminator as part of your objective function, basically you're changing the objective function. So you don't really know what is the objective of training. You're modifying it together with the training itself. And what is amazing is that this works, or at least in some cases. And if you can make it work, it can produce incredible results. We are going to say some words about transfer learning and domain adaptation. So, and this is something that human learning does all the time. So, for example, if I learn how to play the piano, I can sing better, and if I sing better and play the piano, I can learn the guitar much faster than I would if I didn't know how to do it. So somehow we are able to exploit previous knowledge, previous learned capabilities to solve a new task. And basically, these tasks of transfer learning arise all the time in many practical applications. So for example, I might have zillions of perfectly labeled, high-quality data with very good supervision for doing the training, but unfortunately the data come from a simulator. So the simulator doesn't really simulate all the intricacies and all the details of the real world. And from the real world, I can take some data, but a very limited amount and very bad labels or no labels at all. Can I actually leverage my capability to learn on simulated data to solve better the real world scenario? And of course, there is no chance to learn a sophisticated model on the real world data because it's too scarce. So basically, this is what transfer learning is about. We are going to see some ideas here as well. Another learning regime that we are going to see, which is some people at least argue that is closer to how we humans learn, is called reinforcement learning. So basically, we have some autonomous agent acting in the world, in some environment. It can observe some parameters of the world. It can act on this environment by performing some action, making some decisions. And as a result, it might receive a reward or a penalty. It might be an instantaneous reward, or it might be some delayed reward. For example, if I'm playing chess, after a certain amount of moves, if I'm not playing well, I will lose. And this will be a negative reward. So probably what I did is not good, right? So basically, this is kind of frameworks that are used for AI agents, for example, for playing the Go game. And I can actually, by playing many games, I can find best policies to act upon the environment to maximize my reward. And basically, you see many examples of computer games, like Atari games, for example, classical Atari games. Many of the Atari games that computer knows how to play much better than human players. Of course, there is some limitation to this approach because we really need to play many games. So if you want to use reinforcement learning, for example, to pilot a plane, it means that you need to crash the plane a zillion of times. And if you simulate this, you can argue that the simulated environment doesn't capture all the details of a real world. If you want to apply it on a real plane, probably it will be too prohibitive to crash it multiple times. So there are some limitations, and again, transfer learning challenges arise here as well. We are going to touch a little bit upon some more modern and to some extent exotic aspects of deep learning. Basically, many types of data arise in an unstructured way. So it's very easy to work with audio signals or images. They come with a nice, evenly sampled Cartesian grid, It's very easy to do convolutions on them, but what happens, for example, if your data are a graph, or some signal or a graph, or just the graph itself? So these are your data, or you have some manifold, some non-Euclidean space on which you would like to do recognition or regression tasks. Basically, how exactly would you generalize such a construction like convolutional neural network to this kind of data? So we'll discuss some possibilities. For example, we will see that if we translate the notions convolution to the spectral domain, to the Fourier domain, well, we know that convolution becomes product in the Fourier domain, right? But basically, a similar notion, unlike the convolution in the space domain, for example, can be constructed on the graph. So we can do products in frequency domain, but we cannot do convolutions because there is no global group structure that the graph is involved in. So we can do basically some more sophisticated things on these non-Euclidean domains. And we'll be discussing lots of applications. For example, we will primarily focus on computer vision and image processing. So we'll see how deep learning achieves state-of-the-art results, for example, in low light image enhancement or super resolution. So remember these, usually I think things like CSI series, where you see 2 pixels in the image and you say zoom in more. I know this guy. So more or less you can do something like this today with generative models. So basically you are hallucinating things. It's not that you really can give a forensic certificate that this is the guy, but it works amazingly well. And there is no magic because you really work in this subspace from which you can generate only faces. So you will always generate a face. And it will be somehow faithful to the data. But still here you can do an upscaling by a factor of 8 and it will look natural. Then using the deep learning techniques, you can take an input image like this that you take with your smartphone. Take, for example, this painting. For example, this painting by Van Gogh, and you generate a new image that has the structure of the image you took and has the style of Van Gogh. And so it's a hack. There are better ways than the original technique that I'm showing here that can be done today, faster and more principled. But I would bet that even 10 or even 5 years ago, you didn't even know how to approach this problem. What is a style? Can we define it mathematically? What is Picasso's style? Something not really well defined. But what is amazing here is that you take a neural network that you train for visual classification, and then you use the representation that it creates to do style transfer. And what is amazing is that it works. Another very basically probably one of the biggest computer vision tasks is object recognition or visual recognition. So it was an unsolved task, and people were saying that computer vision is still so far from solving it. But nowadays, using deep learning, you can do object recognition very well, and you can also do semantic segmentation. You can actually tell which pixels of the image belong to a specific object. And it can be done surprisingly well, much better than we could 5 or 10 years ago. We also discuss applications of deep learning in natural language processing and in building AI agents, like agents that play simple games. And basically, we are going to code these applications. We have home assignments. We'll of course be doing some simplified, more elementary problems, but we'll also have the final project for the course, in which you are welcome to take a much deeper and much more sophisticated problem and solve it end to end. So we'll talk about the formalities in the third hour. Another aspect that we are going to discuss are hardware accelerators for deep learning. And basically, these can be largely divided into 2 parts. So one is accelerating the training process, and another one is accelerating the inference process. And they are fundamentally different. They have completely different needs and completely different performance targets. Will necessarily meet at least some elements of parallel computing. We'll talk about GPUs as a means, as an instrument to accelerate DNA training. GPUs are nowadays probably the overwhelmingly used tool to accelerate training, but you cannot really do it efficiently without understanding the limitations and the benefits of this hardware. So we are going to see how exactly these architectures work, and what are their limitations and what are their strengths. We're going to talk about inference hardware for deep neural networks. How to do inference, and specifically we are going to talk about two ideas or two techniques that can be used to apply deep neural networks in scenarios that are limited by battery power or silicon cost. So one of them is DNN quantization, basically how to do arithmetics in low precision. And the second one is knowledge distillation or teacher-student models. Basically, how can you take a big neural network and use it to supervise the training of a much smaller neural network that will have a very similar performance. So surprisingly, this task doesn't work directly when you train from examples, but when you do this intermediate staging class. So I will just show you a chart in which the accuracy of visual recognition on ImageNet is plotted against the number of bit operations that you perform. So a typical multiply and accumulate will depend as the square of the number of bits, right? Because it's n by n, the square in terms of gates or number of bit operations. So if you take several deep neural network architectures, they will be more or less here. They achieve about 70% accuracy on ImageNet, and they take something like 10 to the 4th billions of bit operations. So it's really, really computationally intensive. Even if you basically because you work in floating points, some specific floating point. But you can employ optimization techniques, basically quantization techniques to decrease this complexity by something like 3 orders of magnitude without compromising the accuracy too much. And basically, this is something that is extremely important for doing inference, especially on low power platforms. And then we'll talk about a little bit about theory. I'm still undecided what aspects exactly, but there are some interesting pieces of theory explaining why this or that aspect of deep learning works. For example, there are very interesting relations of deep neural networks to information theory and statistical mechanics, to sparse data models and compressed sensing. So I did some of my own works in trying to understand these relations. So I will show you some ideas, at least some insights that indicate why deep neural networks work. But basically, this will be, again, this will not be the central part. So the central part will be to actually to get practical hands-on experience with these tools, exercise on real applications, do a serious project, and basically see all the aspects from algorithms to hardware. Okay, so this is the course in a nutshell. I will give the stage to Avi after the break, and then we have basically immediately after the 2 hours of lecture we have the tutorial in the third hour. Okay. 10 minutes.
This is the second part of the presentation for today, and I'll try to give a very fast introduction about architecture for deep learning. I'll do it again in a fast way. Just we will.
Okay, so in this course we are going to speak both about implementation of neural network and the theory. So this is the reason that this is kind of unique course in the sense that we are not focusing only on the application of the theory, but we have tried to cover both the hardware and the software. So I spoke about mostly about the algorithmic, etc., and I'll cover the hardware side. So what I'll cover this time is, first of all, why we should care about computer architecture in these schools, and we'll discuss a little bit a GPU versus a CPU, and you'll see that it is not just a GPU versus CPU, it will be more generic, because then we'll move on special purpose hardware, and what we can expect from the course. This will be the last course. So, few historical notes which are quite important in the sense, and you'll see in a minute why. And so let's start with what we call the old days of computer architecture, that actually the assumption was that every every point of time or generation we can double the transistor, but it is not only doubling the transistors. We can actually get, we can double the speed, we can get double density, and what it really means is that we got a new architecture every 3 to 5 years, but with a minimal impact on the specific hardware feature performance, we could actually double the performance that we could get every generation. It sounds simple, but this is a very key point, that you could actually take the same program, the same optimization, the same code, run it on the new generation, and you can anticipate that in 5 years I will get this performance, that performance. A very famous story is about Microsoft Windows. The first generation was so slow that people jump and say, okay, you know, that you just hit the key and then you can go and take coffee and come back and you see that the mouse is moving. What people didn't notice that until it takes Microsoft to clean up all the bugs, etc., usually it's about 2 years, the hardware was fast enough, actually it kept with the speed of what was needed by the software, and then it becomes a much more useful. Again, this was a very, very important to be able to anticipate the software and the hardware program. So we already mentioned Moore's law, but the real implication of Moore's law again was that you could anticipate the next generation, and so on. The implication was that you can add more value to the user, you can enable innovation, and you can enable new application in markets. And maybe the most important for company was that you can allow to maintain price and revenue. Price and revenue is important not just for the company, because then the company had motivation to give money for research, so actually the academia also gained out. What's happened is that this golden area over, and this is a graph that mistakenly being used by many people, that this is quite old graph right now. It is around 1999. By the way, just to collaborate people, in 1999, we didn't have cell phones, we didn't have Google, we didn't have Facebook. It looks like in the ancient times. No, it wasn't ancient time, but these were the computer and the infrastructure that we had. Most of the things were single core. And again, why single core? Because what the benefit to go to parallel if anyhow in 2 years I will go to double my performance. So what's happened was that we start noticing that the power density is going so far that it will reach the neural reactor and so on. And again, this was not a graph that said that tried to anticipate where the power density will be, but this was a sign that we cannot continue in this direction. We got to this point, and this is very important, because we're facing something very similar these days with a neural network, and I'll discuss it later. But now power starts to be a very important issue, and then what we saw is that in reality, every new generation we can still double the number of transistors on die. We still do it, but we cannot increase frequency. Which means that we cannot get performance out of frequency or out of the process. And the result is, and I'll show you in the minute that we need to go to parallel. And if we need to go to parallel, so this is the reasoning. I will not go to all the reasoning, but if you have the slides and you see that all the equation shows that to double the performance, it costs a lot of power, but to double the size, the cost costs you only twice. So the conclusion was that as long as enough parallelism exists, it is always more powerful to double the number of cores than to increase the frequency. Which sounds great. We have a good solution. Almost. Almost because now the problem, and again, it started the race for multi-core, which is to put as many regular cores on die, and many cores like NVIDIA, they put a lot of small cores on die, on heterogeneous to put both of them. And the problem is that by saying we go parallel, it has a huge cost. But the huge cost right now is that the programmer should be aware of the architecture. So you'll see along all this course that it is not enough to take your application and parallelize it, even though we start having better and better tools to do it, but you need to be aware of the architecture itself, which means that when you go from one generation to another, you need to re-optimize your code. And you know what's happened when you need to re-optimize the code. You just realize that the engineer that you fired yesterday is the one that need to optimize the code for the next generation, and you don't have it. And this is a major problem in real companies to re-optimize code. It's not something which is trivial. So we start understanding that the sort of optimization change from one generation to another, and in order to write an optimal code, you must understand how the hardware works. And this is very, very crucial because most of us are software engineers that don't care about hardware. In this case, we must care about the hardware because there is no one size fits all. And let's take that for a small example, which is the CPU versus GPU, and you'll see how it happens. So, some of us, I hope all of you, knows how CPU works. Anybody don't know how the general, what is caches, etc.? So I believe that at least you heard the terminology. So usually in CPUs we have large caches, we have sophisticated control, and we have a powerful ALU. So why we build the systems in such a way? This is a question for you.
To handle tasks.
To handle?
Handle tasks, not parallel tasks.
So, if you don't have power, so the main point is to, first of all, you want to reduce the latency to memory. In order to reduce the latency to memory, you must have cache memory, and you bring things to be closer to the CPU. Then, what is the next? The amount of parallelism that you have in the system is not big enough. So we have all different types of prediction out of order, etc. All of them aim at increasing the amount of the parallelism that you have. And you have a powerful LU because if you have the data ready, you want to do it as fast as possible. So this is the motivation in general for CPUs. Going to GPU is not just to do something different, but it's based on different assumptions. This is the die of current GPUs. As you can see, the green part is the LUs. We don't have 1, 2, 3. We have hundreds or thousands of small LUs. By the way, NVIDIA are excellent in taking the same term that we are all using differently and then claim victory. Which means that if you look on what NVIDIA declare as a CPU, you find out that if you have a vector operation, so they count every instance of the vector operation as a different CPU. But this is a different story about counting. But even if you ignore all these artifacts, you end up that you have that most of the die is occupied by simple cores. Why simple? Because, first of all, how they dare to put hundreds of thousands of cores on that? Why CPU doesn't? Because GPUs are optimized for very certain type of application. This was the first time that actually people say, okay, we are not going to build a general purpose something. We are going to build something which is good for a set of applications. Imagine what? When people start seeing that it works, so they convert the algorithm to different algorithms so they will fit to the hardware. So it is not always the case that you can take existing hardware and understand how to optimize it. Sometimes you need to think how people will react. But the very basic assumption of GPUs are you have plenty of parallelism, what we used to call inversely parallel applications. And if you have inversely parallel application, you don't need actually to waste energy in order to extract parallelism like in out of order. You have parallelism, so why you want to extract more parallelism? You have it. You don't need even to spend a lot of power for shortening the latency to memory. Why? Because they're doing tricks like multiplexed operations. So one operation wants to go to the memory, it doesn't have the result, so it goes to another one, and it goes to another one, so the pipeline, the operation, because they're in a parallelism. We'll go to all these techniques later on, but just to give you the notion that we can solve the problem by totally different means. So, assuming that you have enough parallelism and assuming that you change the rule of how the software behaves, you can build hardware, that this hardware will be perfect for your needs. So why GPU started in the first place? Because GPU was planned for graphics. And in graphics, most of the operations are per pixel. So you have enough parallelism. And if you don't have enough parallelism, you move to HD. Then you move to super HD, so you increase the parallelism to any amount of parallelism that you wish. So in parallel application, you naturally have enough parallelism, and if you assume that you have enough parallelism, you can build a totally different system. So it is not just the trick of that one thing is smarter than the other, it is a matter of changing the rule of the game. And this is exactly what happened when the people start looking on GPUs and say, okay, but we can use it for other purposes. So GPUs traditionally, or most of the time, they're running in much lower frequency. They use most of the area for computation and not for storage or caches, etc. And still remember that the main limiter that we have today is not the computation, is the power and thermal. And this is something that we need to remember, because previously we said that we need to save power in mobile application, which is true for battery life. But in reality, the frequency of your processor depends on the temperature of your die. Which means that you cannot, even if you put more processor on die, you cannot run them, or all of them, all the time in high frequency, because they reach the maximum temperature that which is allowed. After some certain, if you reach this temperature, what's happened? meltdown. Meltdown right now it's a virus, but yeah, it go back to sand. And it is very expensive. So the point is that again, in software and in hardware, today you are limited by the thermal point. And if you're limited by the thermal point, so you must preserve the energy, you must consume as little energy as you can for both high end and low end. It is not just for the low end, it's everywhere. If you want your application, when we talk about deep learning and so on, if you want your application to be efficient, meaning run as fast as possible, you must reduce your energy consumption so you can increase the frequency, then you will get more performance. This is a little bit tricky, but this is the trade-off that we have today. This is half of the story. This is half of the story because actually I wanted to expand this, so I left a few slides blank, but since we are running out of time anyhow, so I'll skip it quite fast. The point is that today when we talk about power consumption, and I'll go to it in a minute, power consumption is not only CPUs, or the processing. This is something which is mistakenly assumed. We are paying today a lot for data movement. In a minute I'll show you the numbers, they are quite astonishing. And usually in the general purpose world, we used to assume that either you are doing computation or you are doing, you are either memory bound, which means that you are doing a lot of transfer between the memory and the CPU, or you are CPU bound, which means that you have all the data and you crunch. When we look at on the specific application of GPUs or the specific application of DNN or other machine learning, we find out that we succeed somehow to be memory bound and CPU bound at the same time. We need to transfer. What we are doing is we do things in parallel, but we are moving data all the time and we process it. So we need to be very careful to design a system in such a way that can consume, do the operation in an efficient way and the data movement in a very efficient way. Which means that if you look at it, the way that we build general purpose computers don't fit to the world of the machine learning. But we want to run machine learning applications on CPUs, so what we're doing, what we can do. So we are putting accelerators. So we are putting certain accelerators that aims to accelerate different operations. As I also mentioned before, if you look on the basic ISA of machine learning, is Mach and a few other operations. Very small amount of primitives that you need to actually accelerate. So there is a lot of room because we have plenty of parallelism, and because the primitives that we want to accelerate are relatively simple, there is a lot of room for innovation and for building architecture that will be fit to the application that we are running. But there is a big debate right now among the computer architectural world if the era of the general purpose computers is over, or it is another branch that we need both, general purpose and accelerator. But for sure, for machine learning, most of the applications are using accelerators in this form or in other. And we have accelerators which are like in data center, which are special hardware. For example, in Microsoft data center, they have racks for FPGAs, and these FPGAs are doing machine learning, which is the special hardware that they build for accelerating the general purpose operation that runs on the general purpose processors. And in Google, for example, they build, and we'll discuss it later on, things that called TPU, which is special purpose how they develop for deep learning. So we have extremes, and we'll discuss them later on. So why do we care about how the machine learn? So this is the picture, the picture that I think that many people don't really understand the trend here. Look, this is the energy consumption. Remember, energy is the main point that we want to optimize. Because energy equal to power equal to frequency at the end of the day. So, in order to do add operation in 8 bits, you need only 0.03 picojoule. In order to do the same add, integer add, for 32 bits, so actually you need about 3 times more than 8 bits, which looks reasonable. But surprisingly, the floating point is not, it is 4 times more than the integer add, but it is the same order of magnitude, and the 32 floating point add is 0.9. And we have all the numbers, but let's go all the way down and see how much data movement actually costs me. So to read something from the SRAM is the cache. That we assume that it is very efficient because it is fast and it is near the memory.
To read 32 bytes, a bit, sorry, from SRAM, so it cost me 5 picojoule, which is 10 times more to make an operation. Or it is only 5 times then to do the floating point operation on the same size. And to do a 32 bit DRAM read, it cost me 640 picojoule, which is much, much higher. So the cost of data movement is much higher today than the cost of the computation. Of course, this is not accurate because it depends on the speed and many other parameters, but given that these are comparable numbers, and usually they are, so actually we see that we must take care about things like to reduce the amount of data movement, and reduce the amount of data movement contribute both to the computation because the floating or the execution units are less stored because they have the data, but also it reduces the power dramatically. And it is also very important to be able to reduce the number of bits that we are using during the operation. So if, for example, if you just look in data, let's assume that you just look on a data base, and in this database you have integer numbers. You find out that about 80% of the memory is filled out with zeros. Why? Because in most of the cases, what you really need are only a few bits. But since the representation of the register in general purpose is 64 bits, so all the integers in the memory are represented as 64 bits, which means that most of the bits are zero. So it is not just that we waste space, but it is even worse because we are wasting a lot of power for being able and being forced to move large amount of data and use only fraction. So now we go back to the algorithms. To use a small number of bits, it is not just to change the type. You need to verify what is the accuracy, you need to understand how the algorithm works, you need to understand when you can do it, when you cannot do it.
You need to understand what is the impact of the results, etc. So even if you are not going to a very sophisticated understanding of the hardware, it is very, very clear that there is a very tight connection between the way that we represent operation, the accuracy that we can get out of the algorithm, and the power that they consume. So if we want actually to end up with algorithm that will be very, very power efficient, we need to make sure that we are using the minimum number of bits that gives us enough accuracy. By the way, unlike most of the things that we are doing in computer science, that we try to achieve the best of, and we are very proud to publish this, is the theoretical limit, etc., etc. In real engineering, we never try to achieve the best. Which means that I can build a perfect laptop for you that will be much, much better than the existing laptop. But it will cost you $10 million. I'm not sure how many people will pay the price for this laptop. So the point is that you need always to find out the way to build the best product or the best algorithm or to achieve the best whatsoever, assuming constraint. And by the way, price is constrained, power is constrained. So the game here is usually how to achieve the best accuracy for a given budget of power and for a given architecture that we have. So the game here will be, and we'll discuss it through the course, the game will be to understand exactly how things are working in order to make them very efficient. So this is just a very high level. I will not go to all the details because these are things that we will address them during the course, etc. But let's look on the size. This is the size of data that we are using. This is the total weight. This is not the data itself, the picture itself, but these are the weights. So even in the past, we went for weight which were 60K. And the accuracy, where is the accuracy? I cannot find here the accuracy, but the accuracy was quite low. So actually, right now, and we need the total maps, which are the basic operations that we use for a picture, we need something like 341K. We go in this, in the V1 or in the VGG. In this one, we actually improve it a little bit. But we go to 138 meg data that we need to use to actually use for weights, and we are doing 50.5 gig map operations, which is tremendous. By the way, this is newest algorithm, and when people realize how inefficient this one, they try to generate something with it will be more efficient. So this is the case. So again, we cannot ignore the hardware, we cannot ignore the efficiency, and this is what we try to achieve. So who works on hardware for machine learning? So I think that almost everybody in the field are working on it, which means that if you go to any conference, it doesn't matter what is the subject, you find different sessions on hardware for machine learning. Most of these works are quite incremental, but there are a lot of work, and all the companies are working on this. So let's name some of them. Intel actually target the Intel KLN, what they call, I think that they already killed the project, but they had special architecture, that this architecture used to have
72 in all the cores with accelerators for machine learning. This is part of the family of the Zan 5 processor. In a recent, very soon, they are going to announce a new extension for the ISA for machine learning. I assume that this is what we know right now. This is the exact definition. So I assume that till the end of the course they will reveal it. So this is what we'll know. So wait a minute, in a few weeks I believe that most likely after Passover or something around it we'll get more information. But Intel are very involved in designing new extension and new architecture that will allow you to run things on a general purpose and machine learning. By the way, there is a lot of reason to do it because your machine learning is only part of the entire application. So you want the entire application still to use the general purpose capability to continue to use Linux or Windows or whatsoever. And when you run the application, and the application can be part of your big application or the algorithm, so you want to run this algorithm as efficient as possible. So if you look on NVIDIA has multiple products around machine learning. It started with the Pascal project. Pascal has a lot of new invention, but one of the most interesting part is that they realize that PCI Express is not fast enough. Again, machine learning is not only about transfer data, so they moved to NVLink, which is about, I think, 4 times faster than PCI Express. But they also has a lot of other extension. Maybe we'll discuss it. They announced the Volta project with another extension for machine learning, and now they are using NVLink 2, which is 300 gigabytes per second. They increase the speed to memory. They have this DG1 rack, by the way. This is a little bit old, but people that want to experiment it, as far as I know, they give some time for algorithms. If you want to check your algorithm, they have open. You can get some time to run your application on it. And but the new trend in hardware is to try, or at least to move to FPGAs. I'm not going to detail what FPGA is, but FPGA, in very general speaking, is a way actually to tell the hardware almost at the level of the bit how to manipulate bits. And they can do it in a very efficient way. So why FPGAs seems to be so fit to machine learning? Because now you are not limited to a certain size of a register. You're not limited to a certain size of operation. You can actually decide if you want to work in 1 bit, or in 2 bits, or in 4 bits, or in 8 bits, and it depends on your algorithm. So you can map your algorithm on the FPGA, and you actually cast your hardware in a way that you can be as efficient as possible. Of course, you are paying because this is something which is programmable. So there is a lot of effort to use FPGAs. We still hope that at one point Intel will, we have here a few FPGAs, and recently a paper we wrote about using FPGA for machine learning was accepted for publication, but this is the latest version of Intel that also include CPUs and FPGAs integrated. Xilinx has same design that gives you a lot of flops and a floating point, and you can use the reprogrammable. And this is a very, very interesting direction that most likely will have a lot of contribution. So why we are not moving everything to FPGAs? Two reasons. Cost, they're quite expensive, and the effort to program it is very, very difficult. Because we are programming FPGAs up until a few years ago, you could program it only in hardware language, which is not very convenient to people in computer science or scientific, etc. Quite difficult to write and to debug. Recently, there is a huge effort to write applications to FPGA using high-level languages. They are still not efficient enough, but it's starting to be closer. So, right, and there are FPGAs that are much less expensive. So we start seeing a lot of applications move to FPGAs in this way. And of course, if we can go, if we anyhow work in our system as close to the hardware, so we can build a special purpose hardware, and there are few proposals for it. These are really ASICs that people build. So one good example is the data flow processor. The other one, again, it is a kind of implementation of this one. You can actually program them using what used to be called in the past systolic arrays. They are well-known method, not easy, but it can be done. Recently, Google came out with a new accelerator for machine learning. It is called TPU, and actually they have TPU2 right now. We have only partial information about it, but we know that they already demoed it for driving autonomous cars. We know they're putting them in data centers, and they have huge teams that all the time work in order to improve it. We will have at least one class that will talk about TPUs and similar architecture, and we'll try to discuss the trade-off between to have a special purpose architecture and something which is a little bit more general purpose, but still very efficient for that type of application. And TPU is one of the good examples. Another problem that we have is the DRAM, and right now we start seeing it really stacking in order to get much more bandwidth to the die. It solves some of the bandwidth issues. We'll discuss it later on. Again, so these are the architecture in general that will try, if not to focus, so at least to talk in much more details about how they are implementing them, but also we hope to show the connection between the software, the algorithm, and the hardware, and the accuracy. So again, the outcome of the course should be not just to know how to use tools, and not just to understand how the algorithm works, or at least to understand that we don't understand how it works. But we also want to emphasize on practical things, which is how we can run them in the most efficient way on a proper hardware in order to achieve the best result, because we believe that this is the key for right or good implementation of these algorithms for the future. Questions? Answers? Okay, so I'll